This is the last video from section 4.5 on the topic of rank. In this video, I want to see how we can connect this topic of rank to systems of linear equations. We'll see a big theorem regarding that and a few examples that kind of illustrate the results of this theorem. And then we will see a big summary of all these big topics we've been talking about lately. So let's look at this theorem here, Theorem 4.17. It says, consider AX equals B a system of M equations and N variables. Right, so that really just means this matrix A is M by N. This X is like a column of our unknowns, and B is a constant column. If the augmented matrix and the coefficient matrix, so the augmented matrix here just looks like, A augmented with B. So this first part saying if the augmented matrix, this guy A augmented with the B column, and the coefficient matrix A itself have equal rank R, and that rank R equals N, the number of variables, then the solution to this system is unique. If the augmented matrix A augmented with B and the coefficient matrix A itself have equal rank R, but now R is less than N, less than the number of variables, then there are going to be many solutions to the system. And finally, if the augmented matrix and the coefficient matrix do not have equal rank, then there's going to be that'll be a situation where there's no solution. So I want to see some examples that really kind of illustrate what this is saying and maybe give you a better sense of it than just reading it. But maybe we just mention kind of the big idea behind a theorem like this is that in this system AX equals B, this matrix equation, that's really a system of linear equations, we're really going to think about this matrix A in terms of its column vectors, A1, A2, all the way out to AN, since it's got N columns. You'll have up to N of these A vectors. We're going to call these, this matrix of unknowns, we'll call that a column X1 through Xn. And this matrix of constants over here, we'll call that a column B1 through Bm, but I'll also call that just a vector B for simplicity in some places. So notice if we were to write the system AX equals B, that's just the same as writing this column, is writing this column, all the way out to the nth column vector. Those in a matrix times these x values in a column vector equals this constant vector. Right. But if we take a look at this matrix multiplication on the left, we've seen something about this before, how we can view matrix multiplication with a column vector to the right. We can view this as really just being the first scalar in that column vector times the first column of the matrix, plus the second scalar times the second column, all the way out to the last scalar right here. And on the right side, we have still just this column vector B. Right. So what we're really seeing here is that the solution x1, x2, xn, the solution to this AX equals B system, the AX equals B system we started with, is really just the scalars you need to make B out of a linear combination of the columns of A. All right, so let's say something about that. The scalars in the linear combination, or I'll say, sorry about that. And my pen is not working. There we go. Okay. The scalars in a linear combination of the columns of A the scalars in a linear combination of the columns of A that equals B are the solution vector. So this is just saying exactly what I was describing earlier, that if we can find a linear combination of the A vectors, the columns of our matrix A, that equals this B vector, the constant on the other side, then those scalars we get in that linear combination are the solution to the system. And so we've seen some stuff about this. Keep in mind, the column space of A is all such linear combinations of the columns. So we could say if B is in the column space of A, then by definition of column space, there is a solution, set of x values, to the system. Right, because if B is in the column space, that means by definition it can be expressed as a linear combination of the columns of A. Whatever scalars you need in that linear combination, those would make a solution to your system. Now the question is, when is that unique? The solution is unique if the columns are independent, linearly independent. I should say if all the columns of A, let me fix this up, of A. The solution is unique if all the columns of A are linearly independent, because in that case, right, we already know the columns span the column space, that's by definition, but if they're also independent, then they make a basis for the column space. In which case, any linear combination of those basis vectors that makes one of these guys in the column space would be unique. We said that these linear combinations that we can express any vector, these linear combination of our basis vectors that we can express any vector in a space, in a vector space as, those are unique. There's only one set of scalars that does it. So we'll say meaning the linear combination that makes this true the linear combination that makes that statement true is unique. And so really with this view of things, of seeing the solution of a system as depending on whether the right-hand side is in the column space of the matrix A, the coefficient matrix, is really what we have to think of when trying to prove these statements in this theorem. And so I'm not going to go through more explanation of these statements. I think it's going to be better to see examples that kind of illustrate these statements. So let's jump into one here, kind of keeping this viewpoint in mind where we've got this matrix written as its columns, the x vector of unknowns and b vector of constants on the other side. Let's keep that sort of view of this and try a few examples. So in this example, we're going to be given a system and the REF form, the reduced echelon form of its augmented matrix. We're going to be asked to give the REF, the reduced echelon form of the coefficient matrix, give the rank of the coefficient matrix and the rank of the augmented matrix, give the solution to the system if it exists, and here's probably a very instructive part, express the constant vector as a linear combination of the columns of A if possible. So let's see this first example here. We'll see these go pretty quick here. Yeah, let's look here. So we've got this system, 3x1 minus 3x2 plus 3x3 equals 9, 2x1 minus x2 plus 4x3 equals 7, 3x1 minus 5x2 minus x3 equals 7. And if you write down the augmented matrix for this system, right, just the coefficient matrix with this right-hand side augmented to it, or augmented by it. If you take that augmented matrix and reduce it down to echelon form, you get this matrix. Right. So let's look here and follow these steps that we were asked to follow. First, we were asked to give the REF of the coefficient matrix. Well, keep in mind, the coefficient matrix is just the result of reducing it is just what you get in these first three columns. That last column over here just comes from putting in this constant column. But these first three columns, that's the REF of your coefficient matrix. So let's call this part 1. The REF of the coefficient matrix A is just the first three columns of this REF form of the augmented matrix. Right? So that's easy enough. Part 1 done. Part 2 here, let's remember what we were asking. We already gave the REF of the coefficient matrix, that's this guy. The rank of the coefficient matrix and the rank of the augmented matrix. Well, remember in the last video we said if we've already got these in REF form, the rank is just the number of non-zero rows that we are left with. So let's just write that down really quick. The rank of, I'll say A, is the same as the rank of its reduced echelon form, which is just 2, because we have 2 non-zero row vectors there. And the rank of the augmented matrix, A augmented with B, maybe you write it this way, is this matrix, which also has 2 non-zero vector row vectors, so we just say that's 2. Right. Part 3 says give the solution if it exists. And notice here we've already said the rank of the reduced augmented matrix is the same as the rank of the matrix of the coefficient matrix itself. According to our theorem, let's see what that tells us. The augmented matrix and the coefficient matrix have equal rank R. Is that equal to the number of equations n or less than it? If it's less than, there are many solutions. And let's take a look. In our case down here, yeah, the rank is 2, but the number of equations is 3. 1, 2, 3. So we have the rank of both of these is equal, but less than the number of equations. By our theorem, that says many solutions must exist. And we can find these pretty easily, just the standard way of unpacking this augmented matrix and back solving. If I do this real quick, I get x equals 4 minus 3r, x1 does, x2 equals 1 minus 2r, and x3 equals r. I guess this is the solution. So that's part 3. Give the solution if it exists. Now that's saying you get an answer for any value of r. You get a set of x1 through x3 that satisfies your system. So let's see if we can go just a bit further here. The last little part asked us to write the constant vector 977 as a linear combination of the columns of that coefficient matrix. So we want to write 977 as a linear combination of those column vectors of that coefficient matrix 3, 2, 3, -3, -1, -5, and 3, 4, -1. Well, we said that these x values are exactly the scalars you need to write the right-hand side as a linear combination of the columns of your coefficient matrix. So plug in any value of r up here. Maybe r equals 0 is an easy one. If we do that, we get, if r is 0, you get x1 is 4, x2 is 1, and x3 is 0. So that is a group of scalars that you can attach to these columns to make a linear combination 977. So we can write this real easily now. x1 is 4 times the first column plus x2 is 1 times the second column plus 0 times that last column. We don't even really have to write this. That linear combination will equal our right-hand side, our constant column. Okay, it's just summarizing there. So these actually aren't too bad. Now that we see how this works, let's go ahead and run through the last two real quick. I have a couple more prepared here. Let's see if I can bring those up. Oops, a little far. Let's do this one real quick here. We got another system, x1 plus 4, x2 plus x3 equals 2, and so on. If you take the augmented matrix for this system and take it to reduced echelon form, you get this matrix over here. And let's run through these steps real quick. First thing we were asked to do is give the REF form of the reduced echelon form of the coefficient matrix. We already saw that's just the first 3 columns over here. So let's jot that down really quick. The REF of the coefficient matrix is just the first 3 columns of the augmented matrix REF. So that's part 1. Part 2 says give the rank of both of these matrices, the REF of the augmented matrix and the coefficient matrix. Well, this will be pretty easy. Let's take a look. We can say rank of the coefficient matrix we just look at the rank of this guy, which is already in REF form. So the rank is just the number of non-zero row vectors. So it's 2. But we can see the rank of the augmented matrix, which I usually write as A augmented with B. Well, this is the REF of that augmented matrix. That has 3 non-zero rows, so the rank of this guy is 3. And now maybe we can see why our theorem up there said that when the rank of the coefficient matrix differs from the rank of the augmented matrix, you get no solution. Because what we have here is, if we were to unpack our system, that last row gives us 0 equals 1. Not true, so there's no solution. It's inconsistent. And that's just what the theorem predicts, right? It doesn't predict, tells us is absolutely true. If the rank of the coefficient matrix is not equal to the rank of the augmented matrix, you'll get no solution. And so from here, let's quickly look at, I guess let's just call this part 3, finding the solution. We already did it. There is no solution. Part 4 of the problem said, oops. Just a sec. Computer's catching up with me here. Part 4 says write the right-hand side as a linear combination of the columns of the coefficient matrix, which would be 1, 1, 2, 4, 2, 6, 1, negative 1, 0. But we saw that any linear combination of these guys that makes this vector, this right-hand side, those scalars in that linear combination would be the solution. We have no solution, so there can be no linear combination of these columns that makes the right-hand side. So we can say impossible. Done. Last one here. I think this will also go pretty quickly. Let's just run through it very quick. Let's see here. This one, we have another system, x1 plus x2 plus 3x3 equals 6, and so on. When I take that augmented matrix for that system and reduce it down, sorry, let me pull back down a little bit, and reduce it down completely to reduced echelon form, this is the augmented matrix that I'm left with. And so right away we can say, first part, asking us to write down the REF of the coefficient matrix. We can do that right away and just take, again, those first 3 columns, which in this case looks like the identity. Part 2 says write down the rank of both the REF of the augmented matrix and the coefficient matrix. Both cases, these are REF, so we just need to look at the number of non-zero rows. That's 3 for the augmented and 3 for the coefficient matrix. Let's write that. The rank of both A and A augmented with B is 3. 3 non-zero rows in both of those REF matrices. Then what does our theorem say? Take a beat there and take a look back if you like. But our theorem then says that since these have the same rank, the augmented and coefficient matrix have the same rank, and that rank is 3, in that case this actually equals n, the number of equations. There's 3 equations and the rank of both of these matrices is 3. That is the case in that theorem that's going to tell us we have a unique solution. Let's say our theorem implies a unique solution. So let's find it. Well, this is easy. We've already got the REF form of the augmented matrix. We know how to unpack this and write the solution of the system. It's very simple. x1 equals that first entry in the right column, x2 equals 1, and x3 equals 2. Right? That's our solution, but that also gives us the answer to part 4, where we want to write the right-hand side as a linear combination of those column vectors of the coefficient matrix. Well, we know those x values we just found are exactly the scalars we need to make that linear combination out of these vectors. So if we've solved the system, we're done. We just have to write x1 times the first column plus x2 times the second column. Let's see if I can fix that real quick. Maybe it'll catch up with me. Plus x3 times the third column. There, it went catching up with me. There we go, fix that up. And that is the linear combination of these vectors that equals the right-hand side. Right. So that's the solution for that part. Okay, just a quick summary of the big things. That's the end of this example. Let's just go through a quick summary of all the different sorts of things we've seen lately here. A lot of moving parts. Maybe we can put some of them together. Well, let's see what we have here. Let's see. So here's a summary that your book actually calls a theorem. These aren't maybe perfectly obvious, but we'll take them for granted after we have this theorem. Theorem 4.18 says, let A be an n by n matrix. We have a square matrix here. All of the following statements are equivalent. First, the determinant not being 0, this matrix being non-singular. That's the same as saying that A is invertible. We've seen that before. This is also the same as saying that A is row equivalent to the identity, the n by n identity. We have also seen that before. We have also seen that invertibility means this thing's got a unique solution. Maybe the connections to other statements here isn't as clear, but we've seen some of these connections before. The last two are fairly new for us, though. If all these other things are true, if any of these other things are true, it's the same as saying the rank of A equals n. Right? And that kind of makes sense because we have to have, in order to have a unique solution in that theorem we just saw, we had to have the rank of A was the same as the rank of the augmented matrix, and they both had to be n, the number of equations. So that kind of makes sense. It's all adding up that you'd have a unique solution. Last, the column vectors of A form a basis for Rn. Well, that kind of follows easily, or makes sense very easily from part E here. If the rank of A is n, then the basis for the column vectors, right, the dimension of that column space, which is just the number of vectors and a basis for the column space, that is your rank n. So you know you have n vectors in this basis for the column space, but you're only covering an n-dimensional space Rn. You know n vectors that span a space will be a basis for it if it's got dimension n. So it all kind of adds up here, but maybe these are nice ways to think of all the different ideas we've discussed, but all in one place together. That's it for section 4.5. More videos coming soon.